In microeconomic theory, an indifference curve is a graph showing different bundles of goods between which a consumer is indifferent. That is, at each point on the curve, the consumer has no preference for one bundle over another. One can equivalently refer to each point on the indifference curve as rendering the same level of utility for the consumer. In other words, an indifference curve is the locus of various points showing different combinations of two goods providing equal utility to the consumer. Utility is then a device to represent preferences rather than something from which preferences come. The main use of indifference curves is in the representation of potentially observable demand patterns for individual consumers over commodity bundles. There are infinitely many indifference curves, one passes through each combination. A collection of indifference curves, illustrated graphically, is referred to as an indifference map. History. The theory of indifference curves was developed by Francis Isidro Edgeworth, who explained in his book Mathematical Psychics, an essay on the application of mathematics to the moral sciences, a €1,881, the mathematics needed for its drawing. Later on, Vilfredo Pareto was the first author to actually draw these curves, in his book Manual of Political Economy, 1906. And others in the first part of the 20th century. The theory can be derived from William Stanley Jevons' ordinal utility theory, which posits that individuals can always rank any consumption bundles by order of preference. Map and properties of indifference curves. A graph of indifference curves for an individual consumer associated with different utility levels is called an indifference map. Points yielding different utility levels are each associated with distinct indifference curves, and these indifference curves on the indifference map are like contour lines on a topographical map. Each point on the curve represents the same elevation. If you move off an indifference curve traveling in a northeast direction, you are essentially climbing a mound of utility. The higher you go, the greater the level of utility. The non-satiation requirement means that you will never reach the top, or a bliss point, a consumption bundle that is preferred to all others. Indifference curves are typically represented to be defined only in the non-negative quadrant of commodity quantities. Negatively sloped. That is, as quantity consumed of one good increases, total satisfaction would increase if not offset by a decrease in the quantity consumed of the other good. Equivalently, satiation, such that more of either good is equally preferred to no increase, is excluded. U, in the third dimension, does not have a local maximum for any x and y values. The negative slope of the indifference curve reflects the assumption of the monotonicity of consumers' preferences, which generates monotonically increasing utility functions, and the assumption of non-satiation. An upward-sloping indifference curve would imply that a consumer is indifferent between a bundle A and another bundle B because they lie on the same indifference curve, even in the case in which the quantity of both goods in bundle B is higher. Because of monotonicity of preferences and non-satiation, a bundle with more of both goods must be preferred to one with less of both, thus the first bundle must yield a higher utility, and lie on a different indifference curve at a higher utility level. The negative slope of the indifference curve implies that the marginal rate of substitution is always positive. Complete, such that all points on an indifference curve are ranked equally preferred and ranked either more or less preferred than every other point not on the curve. So, with no two curves can intersect. Transitive with respect to points on distinct indifference curves. That is, if each point on I2 is preferred to each point on I1, and each point on I3 is preferred to each point on I2, each point on I3 is preferred to each point on I1. A negative slope and transitivity exclude indifference curves crossing, since straight lines from the origin on both sides of where they crossed would give opposite and intransitive preference rankings. Strictly convex. With convex preferences implied that the indifference curves cannot be concave to the origin, that is, they will either be straight lines or bulge toward the origin of the indifference curve. If the latter is the case, then as a consumer decreases consumption of one good in successive units, successively larger doses of the other good are required to keep satisfaction unchanged. Assumptions of consumer preference theory: preferences are complete. The consumer has ranked all available alternative combinations of commodities in terms of the satisfaction they provide him. assume that there are two consumption bundles A and B each containing two commodities X and Y. A consumer can unambiguously determine that one and only one of the following is the case: A is preferred to be A PB, B is preferred to A BPA, A is indifferent to B AIBNOTE. That this axiom precludes the possibility that the consumer cannot decide, and that a consumer is able to make this comparison with respect to every conceivable bundle of goods. Preferences are reflexive, means that if A and B are identical in all respects, the consumer will recognize this fact and be indifferent in comparing A and B, A equals B or AIB. Preferences are transitive: if A PB and B PC then A PC. Also AIB and BIC then AIC. This is a consistency assumption. Preferences are continuous: if A is preferred to B and C is infinitesimally close to B then A is preferred to C, A PB and C are B or A PC. Continuous means infinitely divisible: just like there are infinitely many numbers between 1 and 2, all bundles are infinitely divisible. This assumption makes indifference curves continuous. Preferences exhibit strong monotonicity: if A has more of both X and Y than B then A is preferred to B. This assumption is commonly called the more is better assumption. An alternative version of this assumption is strong monotonicity, which requires that if A and B have the same quantity of one good, but A has more of the other, then A is preferred to B. It also implies that the commodities are good rather than bad. Examples of bad commodities can be disease, pollution, etc., because we always desire less of such things. Indifference curves exhibit diminishing marginal rates of substitution. The marginal rate of substitution tells how much Y a person is willing to sacrifice to get one more unit of X. This assumption assures that indifference curves are smooth and convex to the origin. This assumption also set the stage for using techniques of constrained optimization because the shape of the curve assures that the first derivative is negative and the second is positive. Another name for this assumption is the substitution assumption. It is the most critical assumption of consumer theory. Consumers are willing to give up or trade off some of one good to get more of another. The fundamental assertion is that there is a maximum amount that a consumer will give up, of one commodity, to get one unit of another good, in that amount which will leave the consumer indifferent between the new and old situations. The negative slope of the indifference curves represents the willingness of the consumer to make a trade-off. There are also many sub-assumptions: irreflexivity, for no X is XPX, negative transitivity, if XNOTPY then for any third commodity Z either XNOTPZ or ZNOTPY or both. Application: consumer theory uses indifference curves and budget constraints to generate consumer demand curves. For a single consumer, this is a relatively simple process. First, let one good be an example market, for example, carrots, and let the other be a composite of all other goods. Budget constraints give a straight line on the indifference map showing all the possible distributions between the two goods. The point of maximum utility is then the point at which an indifference curve is tangent to the budget line. This follows from common sense: if the market values a good more than the household will sell it. If the market values a good less than the household will buy it. The process then continues until the market's and household's marginal rates of substitution are equal. Now, if the price of carrots were to change, and the price of all other goods were to remain constant, the gradient of the budget line would also change, leading to a different point of tangency and a different quantity demanded. These price/quantity combinations can then be used to deduce a full demand curve. A line connecting all points of tangency between the indifference curve and the budget constraint is called the expansion path. Examples of indifference curves. In Figure 1, the consumer would rather be on I3 than I2, and would rather be on I2 than I1, but does not care where he/she is on a given indifference curve. The slope of an indifference curve, known by economists as the marginal rate of substitution, showed the rate at which consumers are willing to give up one good in exchange for more of the other good. For most goods the marginal rate of substitution is not constant, so their indifference curves are curved. The curves are convex to the origin, describing the negative substitution effect. As price rises for a fixed money income, the consumer seeks less the expensive substitute at a lower indifference curve. the substitution effect is reinforced through the income effect of lower real income. An example of a utility function that generates indifference curves of this kind is the Cobb-Douglas function. The negative slope of the indifference curve incorporates the willingness of the consumer to make trade-offs. If two goods are perfect substitutes, then the indifference curves will have a constant slope since the consumer would be willing to switch between at a fixed ratio. The marginal rate of substitution between perfect substitutes is likewise constant. An example of a utility function that is associated with indifference curves like these would be: if two goods are perfect complements, then the indifference curves will be L-shaped. Examples of perfect complements include left shoes compared to right shoes. The consumer is no better off having several right shoes if she has only one left shoe. Additional right shoes have zero marginal utility without more left shoes, so bundles of goods differing only in the number of right shoes they include, however many, are equally preferred. The marginal rate of substitution is either zero or infinite. An example of the type of utility function that has an indifference map like that above is the Leontief function. The different shapes of the curves imply different responses to a change in price as shown from demand analysis and consumer theory. The results will only be stated here. A price budget line change that kept a consumer in equilibrium on the same indifference curve, in Fig 1, would reduce quantity demanded of a good smoothly as price rose relatively for that good. In Fig 2 would have either no effect on quantity demanded of either good or would change quantity demanded from one end of the budget constraint to the other. In Fig 3 would have no effect on equilibrium quantities demanded, since the budget line would rotate around the corner of the indifference curve. Preference relations and utility. Choice theory formally represents consumers by a preference relation, and use this representation to derive indifference curves showing combinations of equal preference to the consumer. Preference relations, let, be a set of mutually exclusive alternatives among which a consumer can choose, and be generic elements of. In the language of the example above, the set is made of combinations of apples and bananas. The symbol is one such combination, such as 1 apple and 4 bananas, and is another combination such as 2 apples and 2 bananas. A preference relation, denoted, is a binary relation defined on the set. The statement is described as is weakly preferred to. That is at least as good as. The statement is described as is weakly preferred to, and is weakly preferred to. That is, one is indifferent to the choice of or, meaning not that they are unwanted but that they are equally good in satisfying preferences. The statement is described as is weakly preferred to, but is not weakly preferred to. One says that is strictly preferred to. The preference relation is complete if all pairs can be ranked. The relation is a transitive relation if whenever and then. For any element, the corresponding indifference curve is made up of all elements of which are indifferent to. Formally. Formal link to utility theory. In the example above, an element of the set is made of two numbers, the number of apples, call it, and the number of bananas, call it. In utility theory, the utility function of an agent is a function that ranks all pairs of consumption bundles by order of preference such that any set of 3 or more bundles forms a transitive relation. This means that for each bundle there is a unique relation, representing the utility relation associated with. The relation is called the utility function. The range of the function is a set of real numbers. The actual values of the function have no importance. Only the ranking of those values has content for the theory. More precisely, if, then the bundle is described as at least as good as the bundle. If, the bundle is described as strictly preferred to the bundle. Consider a particular bundle and take the total derivative of about this point, or, without loss of generality. Where is the partial derivative of with respect to its first argument, evaluated at? The indifference curve through must deliver at each bundle on the curve the same utility level as bundle. That is, when preferences are represented by a utility function, the indifference curves are the level curves of the utility function. Therefore, if one is to change the quantity of by, without moving off the indifference curve, one must also change the quantity of by an amount such that, in the end, there is no change in u, or, substituting 0 into above to solve for dy dx. Thus, the ratio of marginal utilities gives the absolute value of the slope of the indifference curve at point. This ratio is called the marginal rate of substitution between and. Examples: linear utility. If the utility function is of the form then the marginal utility of is and the marginal utility of is. The slope of the indifference curve is, therefore. Observe that the slope does not depend on or, the indifference curves are straight lines. Cobb-Douglas utility. If the utility function is of the form the marginal utility of is and the marginal utility of is where. The slope of the indifference curve, and therefore the negative of the marginal rate of substitution, is then. CES utility. A general CES form is where and. The marginal utilities are given by and. Therefore, along an indifference curve. These examples might be useful for modeling individual or aggregate demand. Biology. As used in biology, the indifference curve is a model for how animals decide whether to perform a particular behavior, based on changes in two variables which can increase in intensity, one along the x-axis and the other along the y-axis. For example, the x-axis may measure the quantity of food available while the y-axis measures the risk involved in obtaining it. The indifference curve is drawn to predict the animal's behavior at various levels of risk and food availability. See also, budget constraint, community indifference curve, consumer theory, convex preferences, endowment effect, indifference price, level curve, microeconomics, rationality, utility possibility frontier, notes. References. Further reading, Beatty, Bruce R. LaFrance, Jeffrey T. The Law of Demand versus Diminishing Marginal Utility. APPL. Econ. Perspect. Pol 28, 263 Euro 271 doi, 10.1111 per joule 1467-9353.2006.00286 exa, external links, Anatomy of Cobb-Douglas type utility functions in 3D, Anatomy of CES type utility functions in 3D.